R is the correlation coefficient, and R squared is the coefficient of determination. R squared tells us the percentage of change in the dependent variable, y, that can be explained by change in the independent variable, x. Let's suppose that we have a scatter plot that looks like this one. And for this particular set of correlated data values, we have an R value of 0.8. If that's the case, then R squared would be 0.64. 0.8 times 0.8. Then what we could say is 64% of the variation in y can be explained by variation in x. So there would be other variables that would cause the rest of the variation, the other 36% of the variation. So this discussion brings up something that is pretty fun to do. Just go to StatCrunch.com and start to explore the data sets that are loaded there. So let's look at height. And we see some different data sets that come up. And here's an interesting one, mother and daughter heights. So we might ask the question, are these variables related? And we can answer that question by clicking Stat, Regression, Simple Linear. I would expect that a mother's height would have a determining factor regarding the daughter's height. In other words, we would have an explanatory variable, mother, and a response variable, daughter. So let's plot the fitted line, and of course, before we ever do any kind of calculation on a correlation coefficient, we would first want to look at the shape of the data and then plot the residuals versus the x values. So let's plot the fitted line and then plot the residuals. So looking at the fitted line, it looks like there is a positive trend here. So in other words, as the mother's height increases, so does the daughter's height. And looking at the plot of the residuals versus the x values, it does look like there is absolutely no discernible pattern here above or below the line y equals 0. So let's go back and look at the correlation coefficient. It is 0.491 if we round to 3 decimal places. And if we square that and we get R squared, then we would get, if we round to 3 decimal places, a value of 0.241. So we would say 24.1% of the variation in the daughter's height can be explained by variation in the mother's height. Let's look at another data set. So we'll click Data, Load, Shared Data Sets. Here's one that says height versus weight. So here we have some baseball players, and we have their height and their weight. So let's see what the correlation is there. So we'll click Stat, Regression, Simple Linear. We expect height to have an effect on weight. So we'll have height as the x variable, weight as the y variable. We can click Plot the fitted line and the residuals. And here, if we look at this line, there's not very many data values here, but we do appear to have a linear trend. And we do appear to have a random distribution of residuals above and below the line y equals 0, although there are not very many data values here. So this may not be a good data set, but looking at what we have, if we round to 3 decimal places, we would say that R is 0.457, and R squared would be 0.208. So we would say that 20.8% of the variation in weight can be explained by variation in height. Here's an interesting one that says height versus head circumference. Again, there's not very many data values here, only 11, but we'll click Stat, Regression, Simple Linear. We might select height as the x variable, head circumference as the y variable. Plot the fitted line. Residuals versus x values, compute. And we appear to have a pretty nice linear relationship here. Again, the residual plot doesn't show any kind of a discernible pattern. We appear to have a random distribution of residuals above and below the line y equals 0. The correlation coefficient is 0.911 if we round to 3 decimal places, and r squared, the coefficient of determination, would be 0.830. So we could say 83% of the variation in head circumference can be explained by variation in height.